we're going to do in this problem is we're going to release a particle at x equals 0.01 times r1, so pretty close to the annulus. I'm going to draw it right here just because I don't want to get messed up in the picture, but there's our distance x. And it asks, find the frequency of the oscillation of the particle, and it has mass m and negative charge q. Frequency of oscillation implies that it oscillates up and down. Let's think about that motion. How are we going to sort that out? And first we'll just back up here to part C. So show at points on the x-axis that are close to the origin, so close down here to the center. The magnitude of the field is proportional to the distance between the center and the point. So we're asked to show that the electric field is about proportional to x as long as x is pretty small. Let's go back to our equation for the annulus. Let's look at the expressions that we had. So here our electric field is a constant times x over the square root of x squared plus r1 minus x over square root of x squared plus r2. So let's write this equation down again, but let's take x outside. So our electric field is sigma times x over 2 epsilon naught 1 over square root of x squared plus r1 squared minus 1 over the square root of x squared plus r2 squared. So now, for our denominators here, the square root of x squared plus r1 squared, if x is really tiny, that's about equal to the square root of r1 squared, which is equal to r1. Likewise over here, if x is a small number, and if it's small compared to r1, then it's definitely small compared to r2, and this expression is about equal to r2. And this is true if x is a lot smaller than r1. So if x is small compared to r1, then this denominator is about equal to r1, this is about equal to r2, and our electric field has an expression of sigma over 2 epsilon naught 1 over r1 minus, and we'll make this approximately equals, minus 1 over r2 times x. All of this stuff is constant, which shows that if we have a small value of r1, electric field is proportional to x, the distance from the ring. Okay, that's walking us right into part D of the problem. We put our point particle right here at the axis. It's free to move. What happens to it? What is the frequency of the oscillation? So let's think about the forces for a second. If we put that mass at that point, it's a negative charge, so it's going to feel attracted to this disk. So let's label this part D. So our force on that little mass is towards the ring, and it's an electric force. So our electric force towards that ring is Q times the electric field, Q times E. And it points towards the ring, so it's down, so we'll go negative Q times E. So we'll put our charge in here, minus sigma times Q over 2 epsilon naught times 1 over R1 minus 1 over R2 times X. If you remember Hooke's law, which says a spring force is minus Kx, then we have a force, we have minus, we have a constant, and we have x. This is like the constant for this motion. You could say that's like a k for this motion, so like a spring constant. And to find a frequency of oscillation, we remember that an angular frequency, omega, is root k over m, and angular frequency is 2 pi times the frequency f. So we can use this expression to solve for the frequency of that motion once it's released. So f is equal to 1 over 2 pi root k over m. K is our effective k right here, so we'll fill that part in. 1 over 2 pi times the square root of sigma q over 2 epsilon naught 1 over r1 minus 1 over r2 square root, and then this whole thing also divided by m. So there's the frequency of that motion.